Let's consider this numerical problem, which is related to quantum theory proposed by Max Planck. The question says that a 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Calculate the number of photons emitted per second by the bulb. So what you are given is a 100-watt bulb, given a bulb which is emitting monochromatic lights. Monochromatic, mono means one, chromatic, it means the bulb is the light emitted by bulb. It contains only one light with only one frequency or having only one wavelength, single wavelength or single frequency. It's not a combination of many electromagnetic radiations light. The white light that is emitted from sunlight, it's not like that. It's a bulb which is emitting a single kind of radiation, electromagnetic wave, having single kind of wavelength, single wavelength and single frequency. And the power of the bulb is 100 watts. So what does it mean by power? 100 watt, it means 100 joules per second. For every second, the bulb is emitting energy at the rate of 100 joules. 1 second, 100 joules, another second, 100 joules. Every second, it is releasing 100 joules of energy. So what the question has given is, they have given the wavelength of the light that is emitted. The wavelength, the length of one wave, like the length of wave from crest to crest or from trough to trough, the length of the length of the wave, the wavelength is 400 nanometer. Nano means 10 to the power minus 9, right? So how will you solve this question? According to Max Planck's energy from any source or source which can emit electromagnetic radiation, it is quantized. It cannot be continuous. It's like it's emits in packets. So the packets means what? It's called photon. So the energy in one photon is proportional to the frequency of the light, and it's given by E is equal to h into nu, where h is the Planck's constant and multiplied by the frequency of the light. Right? This is the basic equation. E is equal to h nu, where h is the Planck's constant, having value 6.626 into 10 to the power minus 34 joule seconds. A very small amount of small number. Planck's constant is a very small number. Next one. What about frequency? Well, we have not given frequency. So how will you do this? We'll convert we will express frequency in terms of velocity and the wavelength. We know that velocity of electromagnetic radiation is equal to wavelength into frequency. So frequency is velocity divided by the wavelength. So instead of writing frequency, we'll write velocity divided by wavelength. Velocity, we know the velocity of electromagnetic radiation and in vacuum is 3 into 10 to the power 8 meter per second, the speed of light, and the wavelength is 400 nanometer, means 400 into 10 to the power minus 9 meter. So when we simplify this, so this is how we get the energy. Energy of one photon is 4.969. It's around 5 into 10 to the power minus 19 joule. Okay, this is the energy packet one photon is having for this particular this particular light. I think 400 nanometer. I think it's violet. It's violet. Whatever it is, it's around 4 into 10 to the power minus 19 joules, or around 5 into 10 to the power minus 19. This is the energy of one photon. So what about number? So the question is saying what we need to calculate is the number of photons emitted per second. So every second, this many joules of energy is emitted by the bulb. So this many joules means how many photons? How many photons will constitute this much? 100 joules. See, the energy of one photon is only this much, small amount of energy, right? So 100 joules means how many photons? How will it do? The number of photons emitted is you divide 100 by the energy of one photon. So it comes to 2 into 10 to the power 20 photons per second. So the monochromatic light is emitting around 10 to the power 20 photons per second, and it has a wavelength 400 nanometer, and the power, and it depends on the power of the bulb, is 100 watt. I hope it's clear.